In this section, we'll discuss population genetics. We'll talk about allele frequency, genotype frequency, and we'll discuss the Hardy-Weinberg equation. So let's assume we have a gene with two alleles, big A and little a. We talked about what alleles are, so remember these are just two different versions of the same gene. May have a mutation in a few nucleotides, may lead to amino acid mutation, something like that. Two alleles, big A and little a. The allele frequency is the fraction of all alleles at that locus that are either big A or little a. So the frequency of the big A we'll call P. This is equal to twice the number of big A homozygotes plus the number of heterozygotes divided by the total number of alleles, which is N, the number in the population, times 2. So that's a lot of words. Let's look at the equation here and just get a bearing on what we're doing. So we're trying to figure out the frequency of big A. We want to know how many people have a big A as one of those two alleles. Well, how do we figure that out? We take the number of people that are big A homozygous. Since they have 2, we multiply that by 2, right? Because we're looking at alleles, not individuals. So 2 times the number of people that have big A, and then we add to that the number of heterozygotes. We don't need to multiply that by anything because they only have one big A. So that will give us the total number of big A's in the population. Now what we're going to do is take that number and divide it by 2 times the number of people in the population. Why? Because every individual has 2 alleles, right? So 2 times the number of individuals will give us the total number of alleles. So now we have the number of big A's divided by the total number of alleles. That gives us the frequency of big A, or P. Now let's look at the frequency of little a. We'll call that Q. Same type of thing. This is equal to twice the number of little a homozygotes plus the number of heterozygotes divided by the total number of alleles. So looking at the equation, again, we're trying to think how many people have a little a, or how many little a's exist in the population. So what we do is we take the number of homozygous recessive, or the number of little a homozygotes. We multiply that by 2 because each of them have 2 a's, 2 little a's. And then we add to that the number of heterozygotes. Again, not multiplying by anything because they all have 1 a, so the numbers are the same. So that's our total number of little a's. And now we're going to divide that by the total number of alleles, which is again 2 times the number of individuals because each individual has 2 alleles. And that'll give us the frequency of little a, or Q. All right? Since there are only 2 alleles, we're only dealing with big A and little a, we can say that P plus Q equals 1. The frequency of big A plus the frequency of little a should equal 1, the total number of alleles, right? So let's look at how we might apply this. In a population of 100 individuals, there are 49 big A homozygotes, 42 heterozygotes, and 9 little a homozygotes. So what is the allele frequency of big A, and what is the allele frequency of little a? Let's look at how we'll figure this out. We're just punching our equation, right? So for the frequency of big A, that's our P. We're going to take 2 times the number of big A homozygotes. We're going to add to that the number of heterozygotes, and then we're going to divide that number by 2 times the population. So we'll have 2 times 49 plus 42, that gives us 140, and divide that by 200, 2 times 100. 140 divided by 200 is 0.7, so the frequency of big A is 0.7. Now we could do that same equation for little a, or we can kind of use our shortcut, which is P plus Q equals 1. We know that P plus Q equals 1, and we know that P is 0.7, so then we just use some simple algebra, and we figure out that Q equals 0.3. Now, let's go into genotype frequency. The genotype frequency is the fraction of individuals that carry each of the possible genotypes. So now we've moved up one step from alleles. We're not talking about the number of alleles, we're talking about the frequency of a genotype. So frequency of big A plus big A, frequency of heterozygotes, and frequency of little a. Okay? Since these are the only possible genotypes, again, we only have 2 alleles, so there's only 3 possible genotypes. It naturally follows that frequency of big A plus frequency of heterozygotes plus frequency of little a equals 1. Now, the genotype frequencies are easily discovered from the Punnett square. We're used to using the Punnett square to determine probability, but I'm going to show you how we can use that Punnett square to determine genotype frequencies as well. So looking at our Punnett square here, we have a heterozygote and a heterozygote, right? The probability of a big A genotype is the probability of allele big A getting assorted with another allele big A, right? So in a population, these probabilities are equal to the frequency of A, right? What's the probability that they'll get a big A? Well, that's the frequency of A. Therefore, the probability or the frequency of big A would be the frequency of A, big A, from one partner multiplied by the frequency of big A, which would be the A from the other partner. So that would be P times P, or in other words, P squared. So the frequency of big A equals P squared. Similarly, the frequency of little a set up the same way. It's the frequency of little a allele from partner 1 times the frequency of little a allele in partner 2, which would be Q times Q. You have Q squared. So the frequency of little a is Q squared. Now the frequency of heterozygosity is determined a little bit differently. Looking at our Punnett square, we see that there's two possible combinations, since one partner could give big A or little a, and vice versa with the second partner. Therefore, to determine the frequency of big A, little a, or the frequency of heterozygosity, it's 2 times the frequency of big A times the frequency of little a, or 2pq. So, in a population where P equals 0.6 and Q equals 0.4, what are the genotype frequencies? Well, the frequency of big A, that's P squared, or 0.6 squared, so that would give you 0.36. The frequency of heterozygosity would be 2pq, 2 times 0.6 times 0.4, which is 0.48. And the frequency of little a is q squared, or 0.4 squared, so that would be 0.16. Now you can go back and check your work, because remember, the frequencies should all add up to be 1. So 0.36 plus 0.48 plus 0.16 come out to be 1, so our work is correct. Now this leads us into the Hardy-Weinberg equation. Given that the frequency of big A plus the frequency of heterozygosity plus the frequency of little a equals 1, then it is also true that P squared plus 2pq plus Q squared equals 1. That's just simple substitution. So this equation is what we call the Hardy-Weinberg equation, and it relates allele frequency with genotype frequency. So this is one of those equations that you're definitely going to want to be familiar with. P squared plus 2pq plus Q squared equals 1. Now how do we use it? Let's imagine a population in which 1% of the individuals have a recessive disease. What percentage of the individuals are asymptomatic carriers of the disease? Interesting question. So first, what is the question asking? It's asking for the carrier frequency, right? And in a recessive disease, that means heterozygosity, right? So the question is asking, what is the frequency of heterozygosity? Or what is 2pq, right? Now, what does the question give you? It gives you the frequency of little a homozygotes. It says that 1% of the population has the disease, and we know it's recessive. So Q squared is what it gives us. So what do we need to calculate? We need to calculate the allele frequencies P and Q. So, just using our numbers here, we know that Q squared equals 0.01, 1% of the population, right? So if Q squared equals 0.01, then Q equals 0.1, just square root, right? Now that we know Q, we can calculate P, right? Because P plus Q equals 1. So if Q is 0.1, then P would be equal to 0.9. Now that we know P and Q, we can calculate the frequency of heterozygosity. That's just 2pq, right? So 2 times 0.9 times 0.1 gives us 0.18. And there's your answer, 0.18 or 18%. So 18% of the population in this question would be carriers for the disease. So let's look at another practice question here. There's a population of 100 individuals. One of the 100 has an autosomal recessive disease. What is the probability that a carrier woman who marries a non-diseased man and has 2 children will have 1 child with the disease? Is it 3%, 5%, 10%, 25%, or 67%? Now this is a very involved question, probably more than you'll see on the boards for step 1. But if you can answer this question, then you'll be able to handle any of the population genetics questions that they'll throw at you. There's multiple steps here, multiple things to consider. So if you can get your way through this one, then you'll be in really good shape. All right? So let's talk about this. What has to happen for this situation to arise? We know that the woman is a carrier. She has to marry another carrier, right? In order for her to have a diseased child, she has to marry another carrier because it's homozygous recessive, right? The other thing that has to happen is that both she and her husband must contribute the disease-causing allele to one of their children. So not only does she have to marry a carrier, but both of those carriers have to contribute the disease-causing allele. Those are the two things that have to happen. Now, what do you need to know? You need to know the probability that she will marry a carrier. You need to know the probability of two carriers having an affected child, and you need to know the probability that one of two children is affected, because that's what the question is asking, right? What does the question give you? It tells you that the woman is a carrier, so she's heterozygous, and it tells you the genotype frequency, F little a, is 0.01, right? 1 out of the 100 individuals has the disease. So let's just break this down one thing at a time. First question, what is the probability of marrying a carrier? The carrier frequency, remember, is 2pq. Q squared is 0.01. We know that Q, therefore, is 0.1 and P is 0.9. These are the same numbers that we worked out in that last problem. So 2pq is 0.18, and 18 of 100 individuals are carriers. Now, we have to take this a little bit further. What is the probability of her marrying a carrier? Since the patient is a carrier, there are only 17 carriers that she could marry, right? There's 18 total in this population of 100 people. We know that the person we're talking about, the female, is a carrier. That means there's only 17 possibilities left that she would marry a carrier, right? Now, so our numerator is going to be 17. Now, total population, is there anybody that we can get rid of? There's 100 individuals in the population. We know that the person she's going to marry can't be her, so that gets rid of 1. And we know that the person she's going to marry can't be the person with the disease, because that's not the question is asking. We has to be marrying a carrier, so we can get rid of that possibility. So the exact probability of marrying a carrier would be 17 out of 98. Now that's a really icky number to be working with without a calculator. So let's just round it, and we'll call it 20 out of 100 and say 20%. So the probability of her marrying a carrier is 20%. Now the next question we had to answer, what is the probability of two carriers having an affected child? Well, we go back to our Punnett square for that one, right? We know from our Punnett square that 1/4 of the offspring of two heterozygotes are homozygous for the recessive gene. So if we have two heterozygotes getting married, then the probability of having a homozygous recessive offspring is 25%, or 0.25. So we have the different probabilities that we need now. We have the probability of her marrying a carrier, and we have a probability of two carriers producing an autosomal recessive offspring. How do we combine these two things? Well, here's the secret. First of all, leave out any condition that you already know is true, or that has a probability of 1. For example, we already know the patient is a carrier, so we don't have to include that into the equation that we're going to use to combine these probabilities. Now, if two conditions both have to occur for the outcome, you multiply the probabilities of each individual thing together. If only one of two conditions have to occur for the outcome, then you add the probabilities. Again, if both conditions have to occur, you multiply. If one of two conditions have to occur, then you add. Let's see how this works for our example. So here, to have an affected child, the patient must marry a carrier, and they both must pass on the recessive allele. Those are two probabilities that have to happen, so we multiply them together. The probability of marrying a carrier, we said, was 20%. The probability of passing on a recessive allele, we said, was 25%. So 0.2 times 0.25 gives us 0.05. That's the probability of these two things happening. That's how we combine those probabilities. Now remember, the question asked that they would have one of two affected children. Therefore, either the first one or the second one must be affected. Since only one of those two conditions have to exist, then we can add those two, right? We figured out the probability for each one individual. The probability that the first offspring would be affected is 0.05. The probability that the second offspring would be affected is the same, 0.05. But the question is asking that either or, one of two. So we will add those probabilities together, 0.05 plus 0.05, to give us 0.1. Therefore, the answer to our question, what is the probability that a carrier woman who marries a non-diseased man and has 2 children will have 1 child with the disease, is 10%, 0.1. Now, if we use this same technique, we can calculate the prevalence of the disease using the carrier frequency as well. We take the risk of a couple, right? A male carrier times a female carrier, okay? 1 out of 5 times 1 out of 5 gives us 1 out of 25, right? 20% is what we said the risk of marrying a carrier was, right? So that's 1 out of 5. So we're just switched from decimals to fractions here. Now the risk of having a child with the disease is 1 out of 4. Remember, this is an autosomal recessive disease. 2 carriers have a 1 in 4 chance of having a diseased offspring. So what's the prevalence? Well, we take the probability that 2 carriers will become a couple, 1 out of 25, times the risk of having a child, 1 out of 4. And we multiply those together, we get 1 out of 100. Remember that the question said that the disease prevalence was 1 out of 100. So working backwards, we can see that this method is correct. So, in using the Hardy-Weinberg equation to answer these types of population genetics questions, there are certain assumptions that we have to take into account for any Hardy-Weinberg equation. No new mutations, no selection for or against alleles, no genetic drift, no gene flow or migration in or out of the population. All of these conditions change the genotype and thus the allele frequencies and disturb the Hardy-Weinberg equilibrium. And since we're talking about an equilibrium here, none of these things can happen in order to be able to make the assumptions of the frequencies that the Hardy-Weinberg equation suggests. For example, assumption number 1 says that there's no new mutations. Spontaneous mutations will alter the allele frequencies and upset the equilibrium. For an example of this, think about a new mutation in a gene that's occurring frequently. If this happens, the frequency of the Q allele would be increasing all the time. Each time you get a new mutation, or each time you get another person that develops this Q mutation, this Q allele would start to go up and up and up. The odds of someone having the Q allele would be dependent not only on their inherited genotype, but spontaneous mutations occurring within their own development and in their own parent's germline. So you would upset the equilibrium because Q would be increasing. Assumption number 2, no selection for or against alleles. Same type of thing. Selection can alter both the genotype and allele frequencies. For example, going back to our Q, let's say individuals with the disease, homozygous recessive or Q-squared individuals, die before they reproduce, or if they are for any reason less likely to have offspring, the allele frequency, this Q, would decline. Why? Because they would be dying before they could pass it on. And therefore, you would see the Q decreasing. Why then can deleterious recessive genes persist? The answer to that question, heterozygote advantage, right? Sometimes heterozygote carriers who don't have the disease have a selective advantage over even the homozygous normal individuals. And this balances the loss of recessive alleles from homozygotes who can't reproduce, allowing this recessive gene to persist. Example here we talked about in another section, the sickle cell trait, right? Heterozygotes are relatively resistant to malaria, giving them an advantage over normal homozygotes, especially in regions where malaria is endemic, so that mutation persists and that state of heterozygosity persists and we don't lose that allele frequency, therefore it can continue on. Assumption number 3 is that there's no genetic drift. Now what's genetic drift? It's this phenomenon where allele frequencies can change by random chance. For example, 2 heterozygotes, instead of having 1 homozygous big A, 2 heterozygous, and 1 homozygous little a children, might have 2 homozygous big A and 2 heterozygote children, increasing that frequency of the big A allele. And this is just by random chance. But in small populations, if this happens enough times, then you can actually shift the frequencies of P and Q. Assumption number 4 states that there can't be any gene flow. So this means that there's no migration into or out of a certain population. Why is that important? Migration from a population will change the allele frequencies if a disproportionate number of a particular genotype move out, or by reverse, migration into a population will change allele frequencies if a disproportionate number of a particular genotype move in. So for these reasons, no population is in perfect Hardy-Weinberg equilibrium. You're not going to find a population where there's no gene flow, no genetic drift, no random mating, and so on, where these assumptions are all met. Therefore, Hardy-Weinberg in the real world is not going to be useful, but it is a good estimation and is useful for population genetics models. So here, just to quiz you, we've got a random pedigree. What type of inheritance pattern are you seeing here? You're seeing every generation, so you would likely say dominant there, and you're seeing an affected mom in the first generation. You're going to see random individuals affected, both males and females, in the second generation, and you're going to see in that third generation, note only the mother is passing it on. So what type of inheritance pattern are you looking at here? You see, when moms are affected, all of the offspring are affected, and when dads are affected, none of the offspring are affected. That's mitochondrial inheritance. And another question for you. Bruton's agammaglobulinemia is A, autosomal dominant, B, autosomal recessive, C, X-linked dominant, D, X-linked recessive, or E, mitochondrial? The answer here is D, X-linked recessive. Remember, Bruton's agammaglobulinemia is one of those immunodeficiencies, and we have lots of immunodeficiencies that are X-linked recessive. So if you're not sure on that one, your best bet would be to go X-linked recessive. That concludes this section of the lecture. Next, we will discuss cytogenetics.